Let's take a look at an example. We're given some vector field G, which is defined as 10 e to the minus 2z times rho in our rho direction and times our z direction. And so what we want to do is we want to determine the flux of this vector field G out of the entire cylinder rho equals 1, z between 0 and 1. And then after we found that, we want to confirm the result using the divergence theorem. So we can kind of think about physically what's happening here. So of course we have this cylinder and we have rho between 0 and 1, so our radius of that cylinder is 1 and our height is going to be 2, so it's varying from z equals 0 to 1. And on that cylinder we're going to have flux coming out of our top, we're going to have flux coming out of our bottom, and we're going to have flux coming out of our sides. And so as we can see, what we're going to end up doing is having three integrals, one for each of those three surfaces. And we can kind of physically think about what our vector field G is looking like. So we can see from this term that as we're getting to higher levels of Z, our vector field is going to be decreasing in our rho and our Z directions. However, in our rho, we have that it's going to be getting a little stronger as we're getting further away from our Z axis. However, eventually this will overcome that if we're at high enough Z values. We don't necessarily need to know that, but I think it's always good to sort of keep in mind what's happening physically with our vector fields. So again, based on this drawing here, what we're saying is that our outward flux, so we've talked about this in a previous video, is our surface integral of G dot ds, and we're going to say that this is equal to the flux psi sub top plus our flux out the bottom, psi sub bottom, plus the flux out of our side. So we're going to end up doing three separate integrals here. So let's look first at our top piece. So we're going to look at this part right here. And so the basic approach is we're going to do each one of these three, and then we're just going to come back and add the three together. So starting with the flux out of the top, we can say, well, at the top, we know that our z is equal to 1. We know that our rho is varying between 0 and 1. And we know that our phi is varying between 0 and 2 pi. And so essentially that makes a disk at the top if we sort of set these parameters here. So that's going to be our disk up here. Okay, so now we want to evaluate that surface integral. So we can say our psi at the top is equal to our integral from rho equals 0 to 1, and the integral of phi equals 0 to 2 pi. Again, because we have a surface, we have this double integral, and this is the integral of G dot ds. So I can evaluate this integral, this G for a z value of 1, because we know that z is equal to 1 here, so I'm going to plug in a 1 right here. And so what that gives us then is we have rho times 10 e to the minus 2 in our rho direction. We have 0 in our phi direction because we don't have a phi component to begin with. And then we have 10 e to the minus 2 in our z direction. And we're dotting that with our differential surface vector. So we didn't mention what that is, but essentially this is going back to what we've talked about before when we talked about differential length, differential surface, and differential volume. So in this case, we're looking at that shaded top disk. Remember that our differential surface vectors are going to point outward if our surface encloses a volume. Of course, it's going to be perpendicular to that surface. So right away from this, we can see our direction is going to be z. Now we just need a differential surface sort of on this disk here. So whether you go back and then sort of rederive that from your dl and cylindrical coordinates, or you just get that from your notes, we can find that in that case that area is going to be equal to rho d phi, and we're multiplying that by our u sub z because it's in our z direction. So how we write that down here is essentially this is just one thing in our z direction. So we have 0 in our rho, 0 in our phi, and then we have rho d phi in our z direction. So of course, doing that dot product, only that z component of our g is going to be coming out. So let's come down here and we can rewrite this. Our flux out of the top is going to be equal to the integral from rho equals 0 to 1, integral from phi equals 0 to 2 pi, and this becomes 10 e to the minus 2 rho, and I'm going to switch these terms around, d phi, d rho, just such that we have this integral with this differential, so just sort of making it a little cleaner mathematically. And so of course we can see there is no phi dependence here, so we can go ahead and do that integral with respect to phi, and it's just going to give us a 2 pi factor. So this is going to become the integral from rho equals 0 to 1 of 10 e to the negative 2 rho times 2 pi d rho. And so, of course, that's a pretty easy integral to do as well, because the only thing depending on rho is this rho here. Everything else is a constant. So that becomes 10 e to the minus 2 times 2 pi, so that's our constant, and then we just have rho squared over 2 evaluated from 0 to 1, and evaluating that gives us 10 pi e to the minus 2. All right, so that is our psi out of the top. So let's move on to our second term, this psi bottom. Okay, so psi bottom. And so here at our psi bottom, so let's first sort of state what our conditions are, the same as we did before. So here we have z is equal to 0, and we have the same variations for rho and phi. So rho is going between 0 and 1, phi is going between 0 and 2 pi. So now we're talking about this disk down here. Now remember, our unit normal vector for our surfaces point outward if our surface encloses a volume, in this case it does. So our unit surface vector is going to be pointing downward in this case. And we're going to have the same differential surface area of rho d phi. So coming down here, we can say that now our ds, we still have the rho d phi, but now that's going to be in our negative z direction. And of course we could just put the negative sign out front of everything as well. All right, so let's evaluate this integral. So we have psi bottom is equal to rho, integral from rho equals 0 to 1, integral from phi equals 0 to 2 pi, and we have the dot product of g and ds. So now I'm going to plug in z equals 0 into my g equation. So I have rho times 10 e to the 0, 0, and 10 e to the 0 in my z direction. And we're dotting that with, and again, the only component here is in our z direction, so I have 0 in rho, 0 in phi, negative rho d phi. Okay, so this ends up being integral from rho equals 0 to 1, integral from phi equals 0 to 2 pi of, and again, we're only keeping this z component here. So we have negative 10, because e to the 0 is just 1. So negative 10 times rho d phi d rho. And again, the 2 pi comes out from our phi integration. So we have negative 10 times 2 pi. Our rho is the only term there, so that becomes rho squared over 2 evaluated from 0 to 1. And plugging that in, we get negative 10 pi. Okay, so there's our psi bottom. So now we're only missing one term, the flux out of our sides. Okay, so let's state what we know about our sides. So our flux for the sides, now we don't have a fixed z value, but rather our z is going to be varying from 0 to 1. Our rho, however, is fixed. Our rho is set to 1, and our phi is still going to be varying between 0 and 2 pi. And so that gives us all of the sides of that cylinder. So we're talking about pretty much everything that's not shaded here. So in this case, we want our surface, our unit normal surface vector to be pointing away, or our differential surface vector to be pointing away from the sides. And so that's going to be in our rho direction. And again, you can go back to your notes to determine the exact sort of differential surface area, but it ends up being rho dz d phi, and as we said, that's going to be in our rho direction. Okay, so let's calculate our flux out of our sides. So that's equal to the integral from z equals 0 to 1, the integral from phi equals 0 to 2 pi. Again, we have this dot product. Now in my g, I can plug in a 1 for rho. So in my rho direction, I now have 10e to the minus 2z. Phi direction, of course, is still 0 because we didn't have a phi component. And z direction, we have 10e to the minus 2z. And that's going to be dotted with. So now our only component is in our phi direction. So we're going to put rho, but that rho is a 1. So I'm just going to write 1 times dz d phi, and then our other two are 0. So we get something that looks like that. And so let me just put a note here. Rho is equal to 1 is why we made that adjustment there. Okay, so evaluating this, we have integral from z equals 0 to 1, integral from phi equals 0 to 2 pi, and the only term now that's going to come out is this rho component of our g. So we get 10e to the minus 2z d phi dz. So evaluating that, we have no dependence of phi here, so that's just going to give us that 2 pi factor again. So we have 10 times 2 pi, that's our constant term. And taking the derivative of the other part, we have our negative 1/2 e to the minus 2z. So from chain rule, that negative 1/2 came down, and that's evaluated from z equals 0 to 1. And we get that that is 10 pi times 1 minus e to the minus 2. So there is our flux out of the sides of our cylinder. So now remember, for our total flux, we just want to add those three terms together. So from the top, we had 10 pi e to the minus 2. For the bottom, we had negative 10 pi. And for the sides, we had 10 pi times 1 minus e to the minus 2. And so as you can see, if we add all of these together, we get 0 net flux out of our cylinder. Okay, so that was, none of the steps were hard, but that was definitely a lot of work to get through that. So now for the second part of the problem, what we want to do is confirm this result using our divergence theorem. And what we're going to see is it's a lot easier and a lot quicker. Okay, so let's start by restating our divergence theorem. So it says that our net outward flux is equal to the surface integral over the closed surface of g dot ds. So that's what we just did, but from divergence theorem we can say that's equal to the volume integral of the divergence of g multiplied by our dv. So now what we're doing is we're evaluating this integral here. Of course, if we want to evaluate that, we need to evaluate the divergence of g. So let's start there. So we know divergence. Let's see if I can write a better del. So del dot g. So we're working in cylindrical coordinates. So we have 1 over rho times the partial of, with respect to rho, of rho times our rho component of g plus 1 over rho times the partial of our phi component with respect to phi, and plus the partial of our z component with respect to z. And so it's very important whenever we have a term like this that we multiply that component by rho before we take this partial derivative. So in this case, this equation then becomes, plugging in our values, we have 1 over rho times the partial derivative with respect to rho of, now our rho component of g coming back up here is going to be essentially this right here. We have 10 e to the minus 2z times rho. Okay, so coming down here, if we're multiplying that by rho, what we end up with is a rho squared times 10 e to the minus 2z. So notice I multiplied that before taking that partial derivative. We have no phi component, so that term is just going to be 0. plus the partial with respect to z of our z component, which is just 10e to the minus 2z. Okay, so now this becomes, we have our 1 over rho out here. If we take the partial of this term in brackets with respect to rho, we get that this is 2 rho times 10e to the minus 2z, plus taking the term, the partial with respect to z of this term, we get that that is 10, sorry, we have a negative 2 coming down, so we have negative 2 from our chain rule, 10e to the minus 2z. And what we can see from that is here our rho is going to cancel out. So there goes our rho dependence. And now we have 2 times 10, so 20e to the minus 2z, plus a negative 20e to the minus 2z, which is going to cancel out, and we have 0. So plugging back into our flux equation, we now have the volume integral of 0, rho d phi dz, so that's our differential volume for cylindrical coordinates. Of course, if our integrand is 0, we're going to have 0 there as well. So as we would expect, we get the same result with a lot fewer work, or a lot less work, I should say. Of course, this worked out to be a little easier. We didn't have to actually evaluate this last integral. If we did, of course, we would have a triple integral for rho, z, and phi, and we would put in the appropriate limits. But again, we're still only evaluating one integral, as opposed to, as we saw here, we had to evaluate integrals for each of the 3 different surfaces.